My name is Parker Lusk, and I'm excited to be presenting our work on global data association using the Grassmannian Manifold. The use of 3D lidar has become a gold standard for navigation in urban settings, but this can require processing millions of points per second, which often leads to large maps that can be difficult to store, load, process, and communicate. Further, the sparse and non-uniform sampling of lidar data makes it difficult or even impossible to identify point-to-point correspondences between scans. ICP and its point-to-plane variants can often be effective, but ultimately they are local algorithms that require a good initial registration guess. When this is not available, ICP can get stuck in a local minimum and fail. This is an issue because revisits detected by lidar place recognition modules can be up to tens of meters away, making ICP ineffective. To overcome these challenges, we propose to use geometric primitives such as lines and planes as lightweight abstractions of the lidar scan. Using geometric landmarks avoids the costs of storing and processing point clouds, enables maps to capture meaningful structure, and improves mapping accuracy. Given this, the question this work sets out to answer is how to find correspondences between lines and planes for geometric verification and registration. While there are some other works in this area, they face challenges and limitations due to the heuristic representation they use. In particular, existing works in matching lines and planes often exhibit sensitivity to noise and are not view invariant. Our approach leverages our previous work on graph-theoretic global data association. To quickly review Clipper's principle of operation, consider trying to align the blue and orange bunny point clouds shown here. The key idea is that the rigid body transformation does not change the internal distance between 2 points of the same point cloud. For example, the distance between the nose and the ear is the same in both point clouds, and therefore the corresponding matches are geometrically consistent. By building a weighted graph that encodes the consistency between pairs of associations, Clipper is able to identify large cliques of consistent matches, even in the presence of many bad associations. To use this algorithmic framework in our case, we need to be able to calculate distances that are invariant to rigid body transformation so that we can build a consistency graph. For example, in the lidar scan shown here, what is the right distance function to use between two infinite planes, or between an infinite line and an infinite plane? Answering this question requires choosing a representation. Common landmark representations include centroid only, which discards additional shape and orientation information and is very sensitive to detection noise, or normal form and closest point form, which depend on the sensor origin and as a result do not meet the desired translation invariance property. Instead, we use a more natural representation for lines and planes, called the affine Grassmannian Manifold. To gain intuition into this representation, first consider lines and planes through the origin. These linear subspaces are in fact elements of the Grassmannian. Given the manifold structure, these geometric objects can be algebraically represented as matrices, and we can adopt the Grassmannian geodesic as the distance function, which can be efficiently computed using the principal angles between two subspaces. Importantly, note that this metric allows computation of distance between subspaces of different dimension, such as lines and planes. Of course, we are really interested in lines and planes detected away from the central origin, and so we represent landmarks as elements of the affine Grassmannian manifold, which can be understood as an embedding in a higher dimensional Grassmannian manifold. This embedding causes affine points to become lines, and similarly, affine lines to become planes. Finally, we note that the naive application of the Grassmannian metric is not translation invariant and can cause distortion. The solutions for these problems are straightforward and non-restrictive, and our paper describes the technical points in more detail. Our graph match algorithm is able to globally match and register line and plane landmarks without any initial guess. By using the affine Grassmannian representation, GraphMatch is able to use the full geometric description of these landmarks. Interestingly, although we do not match lines and planes, because we can calculate the distance between subspaces of differing dimension, we can leverage cross-class distances to improve matching performance. For evaluation, we verify potential loop closures from the lidar data for KITTI sequences. Loop closures are grouped by distance between lidar scans into easy, medium, and hard cases. We compare against recent lidar mapping works that use poles only and planes only for geometric verification. In the next few slides, a grid of 2D histograms like the one shown to the right will appear so that we will compare the methods within each difficulty level. We evaluate registration quality using rotation and translation error. The more yellow that appears in the bottom left corner, the better. In the easy case, we already see pole match breaking down due to the scarcity of pole landmarks in many of the scans. Note that plane match, which uses the origin-dependent closest point representation, performs reasonably well in this regime. However, as the distance between scans increases, plane match also breaks down. In contrast, graph match is able to maintain high performance, increasing recall at 100% precision substantially. We extend the plane match method to include both poles and planes, represented as closest point vectors. In this visualization, we see that the number of correct matches, indicated by green lines, is decreased as the baseline between scans increases. In contrast, graph match is not affected by the baseline distance and is even robust to the detection noise that occurs when detecting planes and poles in each scan. In conclusion, we presented graph match, a method for global matching and registration of line and plane landmarks represented as elements of the affine Grassmannian manifold. This representation enables the use of our robust graph theoretic framework, and we show substantial increase in successful registrations over the prior state-of-the-art. Finally, because feature matching is such a fundamental task, graph match can easily be used in other domains, such as multi-sensor multimodal extrinsic calibration, as shown here on the bottom of the slide. For more details and quantitative analysis, we invite you to read our paper and to reach out with any questions or comments. Thank you.